Okay, good morning, everyone. We're going to be talking in this next session about complex ruptures. Shortly after lunch, and we're going to be talking about splays. But for the rest of the morning, we're going to be talking about complex ruptures. Hopefully everybody remembers from day one what that is. But I want to go over specifically the case for Diablo Canyon. So for the agenda, we're going to look at 3 methods to calculate. I need to change that, sorry, that RMS. But also how the developers handled the complex ruptures, and then we'll go over the Diablo Canyon case. Some of you may remember this from our first workshop. So the first of the methods is to use the parameters to the closest point on the fault. So if we look at the Meyer case, we have 4 different planes, and Tom, I know that this is not your favorite representation of Meyer, but this is just using an example at this time. Okay, we have one rupture here, here, down, and here. So we have 4 different planes. So let's take a look at station A and station B. So if we use the closest point on the fault for station A, we're going to go to a 180 degrees with a dip of 75. For station B, it's minus 90 and 45. And then you compute your GMPE using those. The second method is to use the weighted average, and this is what most folks did, most of the developers use in the NGA West 2 development. And so, for instance, for Meyer, here's all of the different segments. Here's the lengths, the widths, the areas, the rakes, and the dips. And then they did a weighted average based on the length. So that this is what was suggested in the flat file, and many of the developers used the weighted average whenever they computed their GMPEs. So hopefully everybody can see this. Now I'd like to go over how the developers develop their GMPEs, what they use in their GMPEs, and then in a forward modeling sense, how would you utilize those GMPEs if you do have a complex event? So starting with asks 13, he uses his closest point to that segment's rake and dip. It's stated in the paper that way, and he also recommends, or they recommend, that whenever you do any forward modeling, you're still using that closest point to the closest segment of the fault. Ask uses strike slip, reverse and oblique is a bin, and normal oblique are also a bin. Going on to Cho and Young's 13, they use the weighted average, so that's that method 2 that I showed. They have strike slip, reverse and oblique, normal and oblique as well. And again, it's not specified within the paper, but they're recommending to use a weighted average of the rake and the dip within the GMPEs. For Campbell and Besorgnia, again, they use the weighted average. Same style of faulting as previously. They did not specify in their paper how to do a complex event, but they did suggest that we do a study about it. If you know Yusuf, that's actually pretty funny. Okay, for BSSA, they use the weighted average. They utilize strike slip, reverse, normal, and unspecified. So they don't necessarily call out obliques. And so in talking with John Stewart, it's not specified, but they're recommending the weighted average of the rake and the dip and with the RJB distance to the closest segment. For Idris, he used the weighted average. He only uses strike slip and reverse. He lumps normal into strike slip, and there's no mention of oblique. And how to forward model a complex event was not specified, and I didn't get a chance to ask him. For Akar, it's not specified in the paper how it was developed for complex events. But they utilize strike slip, reverse, and normal. And in speaking with them, it's not specified within the paper, but he's recommending the weighted average on the rake and the dip, similar to the other developers. For the GK method, again, it's not specified within the paper how to utilize, but he uses strike slip, reverse, and reverse oblique. Normal is captured in the strike slip. Forward modeling of complex events recommends 2 different methods. The first one is to model as 2 different events. So look at the magnitude and the distance, the style of faulting, term to one segment, look at the same for the other, and then you can SRS them to get your ground motions. Or use the full magnitude of the event and appropriate ratio of the style of faulting terms. So he doesn't use rake or dip, but he has a style of faulting term. For strike slip in reverse and also for reverse oblique. So for instance, if you have half of the fault is strike slip and half of the fault is reverse, then use a 50-50 weighting on those the style of faulting terms. For bindi, it was not specified how it was developed or how to implement in a complex event, but utilizes strike slip, reverse, and normal. And for Zhao, uses strike slip and reverse, and the normal is included in strike slip as well. Okay, so going forward, you'll see between myself and Carola and Katie in the next couple of presentations, we're using different methods to try to get at the complex and the splay faults. So my first method is looking at the closest distance to that segment, using that segment's dip, rake, distance, and magnitude. The second one is like what was utilized in the NJ West 2, where you're looking at a weighted average. This is an example for the San Luis Bay, where you have the San Simeon, the Hosgri, and the San Luis Bay, and then the weighted average for each. Method 3, we're using the weighted average of 1 over R squared for the dip and for the rake. And the response spectrum is computed using those. So just as an example, if you have, this is just for the dip. We were calling it RMS, but that's, basically I've been told it's not really RMS, it's just 1 over R squared. So we'll fix that. So we have one dip multiplied by 1 over the R squared over the sum of the 1 over R squared. So what this means is that even though you might have a very long fault, the closest proximity is going to give the higher average, and it's going to be weighted closer on that one segment as opposed to something that's very far away from your site. The fourth method is going to be the finite fault simulations, and those are going to be available for the March 2014 workshop. Okay, so let's go to Diablo Canyon. We're going to look at 3 different faults. We're going to look at the San Simeon, the Hosgri, and then the San Luis Bay. So here we have a strike slip San Simeon, a strike slip Hosgri, and then we have a reverse San Luis Bay here. The Hosgri actually continues down here, but as we went over on Monday, because this is a complex and not a splay fault, the Hosgri is not going to rupture through here. It's going to come down and it's going to go onto the San Luis Bay. San Luis Bay here is being modeled as a dip of 70 degrees and it's a reverse fault. Okay, so the response spectra for this. Okay, so again, the first method is to the nearest segment, so we're using the 90 degrees and the 70. Even though it's very small and you have a lot of strike slip, we're only using the 90 and the 70 for the entire system. The weighted average, now you're seeing that the rake is now 170 because you have such a great length of strike slip that now we're modeling it as a strike slip and it has a dip of 88 degrees. So you can see the difference in the response spectra. And I'll have some more comparison plots here in a minute. For the 1 over R squared rate, 1 over R squared weight, I challenge you guys to say that fast. We get a rake of 111 degrees. So we're not quite oblique, we're still a little bit on the reverse side. Actually 112.5 would make it closer to oblique, but right now we're still going to model it as a reverse, but now the dip is 75.
Jennifer, can you go back and forth, please?
Okay? Okay, so here's a comparison of those methods. And what I'm going to be comparing to is method 2, which is the weighted average, which is what most of the developers used. So for all periods, we took the residuals between the method 1 and 2 and between method 3 and 2, and that's what you see here. And on the most part, systematically, it's higher, so about 0.4 log normal units is the difference between them, and it's pretty much across all periods. This is for all 9 of the GMPEs that we looked at. Okay. Let's move on to the Los Osos. So again, you have a nice long San Simeon strike slip, very small Hosgri strike slip, and then you have a fairly large reverse Los Osos. Dip is about 60 degrees on the Los Osos, is actually about 4 segments. We're going to model it here as a rake of 90 as an example, but as you can see here for the entire system, you're now picking up a lot more that's reverse as opposed to for just the very short San Luis Bay. Okay, so for the method 1, so to the nearest segment, we're going to say that that's to the Los Osos, so we have a rake of 90 and a dip of 60, and that's what we're going to feed into our GMPEs. If we take the weighted average, we now have a rake of 149, so now we're into an oblique range. So we're going to be comparing that oblique to a dip of 80 degrees. And then if we're looking at the 1 over r squared weight, we have a rake of 96 because you're getting a larger contribution because you're closer to the Los Osos than you are to the Hosgri and the San Simeon. And so we have a rake of 96 degrees and a dip of 62. So between the two, you can probably see that the method 1 and method 3 are probably going to be closer. And so as you can see here again, systematically, between method 1 and 2 and method 3 and 2, we're pretty much higher as opposed to the weighted averages. Okay, so what are the implications on hazard and ground motion, and what does that really mean? So the highest that we found for the differences between the methods was about 0.4 log normal units. And if you take that into a percentage, it's about 150% increase across all frequency ranges. On the high side, the probability of a complex San Simeon, Hosgri, San Luis Bay rupture, if it all goes in that, about 10%. We think that's kind of high, but we just decided to go with 10%. Looking at the hazard, so these are from whenever we were looking at all the different hazard curves from Tuesday. The San Luis Bay contribution to the total hazard at different periods ranges from 20% down to 4%. So if you take all of that and mash it all up, the changes to the total ground motion at 10 to the minus 4 at PGA is about 2%. Changes at 0.5 hertz is about 5% in ground motion.
This is not G, 2%.
No,
Okay.
this is a change. Okay. Okay, for the Los Osos, again, as we saw, it was about 0.4 log normal units again, so it's about a 150% increase. We stuck with the probability of complex San Simeon, Hosgri, Los Osos of about 10%. The contributions here range between 16 and 7.5 for the different periods, or different frequency ranges. And so the maximum changes on the ground motion range between 2% and close to about 5%. I see a lot of people doing this and squinting.
So, I'm sorry. I'll trap. So this is back to trying to keep track of what's important, right? And while you can, what Jennifer showed is we can get a big effect on any scenario. A given deterministic scenario might be 0.4 natural log units or a factor 1.5, and you think, wow, that's a big effect. We need to really pay attention to it. But because the way the faulting works there, if we look at how that will impact our probabilistic results, it's going to happen infrequently, or at most affecting one of these faults that might be contributing 20% to the hazard. So that already limits the total impact that you could have. And then if it's only as high as a 10% of the ruptures are involving this complex rupture, that it's so infrequent that we have a small change to the hazard at the 10 to the minus 4 level. If we went to a 10 to the minus 6 level, then these numbers would go up a bit. But it's still trying to show us what is the size of the effect. This is not small enough for us to say ignore it and just move forward, but it isn't big enough to say this should be the focus of all of our work going forward. The sigma models we discussed this morning are likely to move things more than this is going to move them up and down.
Correct.
So while you're thinking there, what the heck does this mean? That's what she's trying to do. And those numbers, Jennifer talked about, that first row is in probability space, right? So that's like the deaggregation. Okay, contribution to hazard. So 16% of the hazard at PGA is from the Los Osos fault. Okay. Our second table is if you reran the hazard with these effects built in there, how much would the 10 to the minus 4 ground motion have changed? So if you read off going across, it's going to go up a few percent. That's what she's trying to show. They're nodding their heads now,
Okay.
which is better.
Thank you for clarifying.
Is that clear to the, okay.
So one of the things I want to point out is I'm not advocating which method is correct. Corolla is going to be showing a little bit more in the NGA West 2 database, you know, looking at different methods, what might be closer. But she has the next talk, so she'll probably give a little bit more light on maybe which method we should go forward with. And I think I saw a hand in the back.
Chris?
Just curious where the probability of the complex rupture came from. The 10% is not something I'm familiar with. So who came up with that number?
We talked about it. We believe that it was probably somewhere between 5 and 10. And so on the most part, we said, okay, well, let's look at 10 and see what the contribution is from there.
So clearly that's not established yet, Chris, and so it's a number pulled out of the air. It's got to be between 0 and 1, right? Let's put it that way. But I don't think it would be surprising to have every single rupture be this complicated. So if the number was 20%, then you can basically double those effects. Okay? So if that helps you, I shouldn't say double the effect on the ground motion. If it goes up to 20%, so it's twice as much, we take that. So then this number would go up about 30%. So 2 times 1.3, so it'd be maybe a 3% increase. Okay, just the way hazard's going to scale based on the slopes of the hazard curve. So those numbers on the bottom are ballpark. How important is this? Do we really need to focus on this? Is this where we put most of our effort? Is this a moderate effort? Is this if it had been 0.5%, we'd say we'll just we'll be conservative and charge for it and use the largest approach and not worry about it. I think it's a big enough number that it's worth some effort, but it's not worth all of our effort because this takes, with our numerical modeling, we have a limited number of cases we can deal with, and we need to decide, do we focus them on complex ruptures? Do we focus them on splay ruptures? Do we focus them on understanding, hanging wall scaling, or how we get to magnitude 8s and so forth? That's what we're trying to get at with this picture. This isn't to tell you the answer, it's to give us guidance on focusing our discussion and our effort.
And another thing to point out is that the 0.4 natural log units, that's on the high side. So really, when we were looking back at these graphs, 0.4 is on the high side. So really, if you take maybe the median, it's about 0.2 over most of the frequency range. Are there any other questions?
Bob Anderson, Seismic Safety. Getting back to the same bullet item that Chris was looking at, I know the 0.1 is kind of pulled out of the hat. Basically, are you saying for your study there, you're looking at a rupture, a continuous rupture of all 3 of those faults together?
That is correct.
End to end?
That is correct.
Okay.
So some complex ruptures will likely be in the source characterization, like USURF creates complex ruptures, but they're not the typical way the faults are rupturing. They are a possibility, right? And so think of it just as a guideline for the relative importance of this effect compared to other things, nothing more than that.
Any other questions? Okay, thank you.
We can blame Steve and Hans there. Those are the ones.
I was trying not to throw anybody under the bus.